To understand the derivative, first we have to understand the slope. The slope of a line is a ratio of the change in rise over the change in run. On this graph, for instance, we can express the change in run as 2 and the change in rise as 2. Or we could have change in run as 8 and the change in rise as 8. It doesn't matter, because no matter which change in rise or change in run values we choose, the slope will always be 1. This is obvious because the graph is linear. As you know, not every graph is linear. However, as a general rule of thumb, which is not always applicable, a graph will appear linear if you zoom in infinitely far enough. This is the building block of the derivative. Take the f of x equals x squared graph, for example. What if I asked you to find the slope at x equals 1? That is, zoom in at x equals 1 until the graph is linear. What is this slope? Simply enough, we will use the equation from earlier, change in rise over change in run. For our change in run, start at x equals 1 and move to the right by some value h. Now the change in rise is the difference between the function's value at x equals 1 and its value at x equals 1 plus h. Our slope is now f of 1 plus h minus f of 1, all divided by 1 plus h minus 1, or just h. Recall that we zoomed in exceptionally far before this graph appeared linear. Therefore, this h value must be very small. So far, in fact, that we almost consider it to be 0. This is where we introduce the formal definition of the derivative. The instantaneous slope of the function at x equals 1 is the limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h. If we want to consider a point besides x equals 1, we can replace every instance of 1 with some unknown value x. This is one of the two limit definitions of the derivative. The other definition is the limit as x approaches a of f of x minus f of a divided by x minus a. Graphically, this definition comes from taking the slope between x and another point a as we let the value of a approach x. Notationally, you'll see many different variations of the derivative. The big ones are dy dx, df of x dx, d dx of f of x, and f prime of x. These are not gibberish. Recall that the slope equation is delta y over delta x, where delta represents the change in the value. Now we can introduce the term d. Where delta is some change, d specifically represents an infinitely small change. Let's see this in practice. Returning to our previous example, let f of x equals x squared. As mentioned before, the derivative of f at x equals 1, or f prime of 1, is the limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h. Plugging in f, we get the limit of 1 plus h squared minus 1 squared divided by h, or 1 plus 2h plus h squared minus 1 over h. This simplifies to 2 plus h. Since we let h approach 0, the limit is just 2. That is to say, the instantaneous slope of the graph at x equals 1 is 2. If we let x be arbitrary, then this limit becomes f of x plus h minus f of x divided by h, or x squared plus 2xh plus h squared minus x squared divided by h. Canceling the h term, we get 2x plus h. H goes to 0, and we are left with just 2x. Graphically, this tells us that the instantaneous slope at any point x is 2x, or twice that of x. Here, it makes sense to introduce something called the tangent line. To be tangent, the line must intersect f of x at just one point. The slope of this line is the derivative of f of x at that point. To clarify, recall the equation of a line, y minus y1 equals m times x minus x1. If we want to find the tangent line at, say, x equals 1, we plug in 1 for x1 and f of 1, or just 1 squared for y1. Then the slope m is equal to f prime of 1, or 2 times 1, which is just 2. Therefore, our tangent line is y minus 1 equals 2 times x minus 1. This can be written as y equals 2x minus 1. For each x value, there exists a unique tangent line. Here we can see the tangent line in blue as I change the value of x. Tangent lines and derivatives are very similar, but it's important to note that derivatives are a number and tangent lines are geometric objects. I hope you found this as a nice introduction to the world of derivatives and tangent lines. Feel free to send me a message with any feedback, comments, or questions. I'd love if you subscribed, and thank you very much.